Chemistry time. Today we're talking about the organization of one of the most, I think, beautifully, one of the pinnacles of human creativity and analytical thinking, both what some people might have called the right brain and the left brain sides of human endeavor. That is, the artistic and creative and the mathematical and analytical. One of the best fusions of those and the best examples of each and both is the periodic table. The periodic table of the elements. And that's what we're going to talk about today. The objective is relate the structure of atoms to that of the periodic table. Relate the structure of atoms. What is that? What do you think that means? The structure of atoms. Yeah. What it's made of, basically. The atom as a whole, what it's made of. Relate the structure of the atom to the structure of the periodic table. Implying, and in my opinion at least implying correctly, that the way the atom itself is, the nature of the atom itself, is related to the way the periodic table is. And of course, atoms exist outside of human endeavor, right? Like atoms exist not only without needing to be influenced by human beings, but despite that human beings have tried to discover what is going on in the atom, they're kind of still, even to some extent, a little hidden mystery. So, but the atom itself and the way it is influences the way we choose to organize the periodic table. So while this thing, the periodic table, is made by human hands, right? Like this is a human attempt at organizing the way things are in nature. The atom is obviously a component, the base component of nature itself. And so let's diagram a Bohr model down. So this is, if I've drawn this little circle here, what does that probably represent? The nucleus. So this, I'm going to label it the nucleus. And then these circles around it. Remember, this is not a factually accurate way that electrons behave. 4, 5, 6, 7, 8. 1, 2, 3, 4, 5. This is not a factually accurate way of what an atom would look like, but it is a way for us to model the kind of things that exist and happen in an atom. So there's a nucleus made of what subatomic particles? Neutrons and protons, surrounded by electrons that are outside the nucleus. And those electrons are truly organized in energy levels, but they don't look like this. They don't look like planetary orbits. By the way, can we tell what atom this is? Well, certainly we can. We don't know how many protons there are because the nucleus is there, but we do know that there are 2 electrons in the first energy level, 8 in the second, and I think I've drawn 5 in the third energy level. So what element is it? It's 15. It's phosphorus, right? Yeah. So I've happened to draw phosphorus here. So this is the atom phosphorus. It could be something else that has gained or lost electrons, but we'll just say it's the atom phosphorus. Remember, atoms are electrically neutral, so we'll say it's atomic phosphorus. That is, it's a phosphorus atom. And the way that this is my point, is related to the location of the element phosphorus on the periodic table of the elements. I tried to draw this good. Every year I try to draw it good and don't know if I ever quite succeed. I think I actually need one more. What are these? What have I've indicated with these vertical lines here? Columns, which we also call, as I said before, groups or families. And then these, what am I indicating here in purple? Yeah. Kind of drawn a little bit too tall. These then are periods on the periodic table. So the most basic division of the periodic table is into columns called groups or families and rows called periods. So, and we even number them. This might be period 1, 2, 3, 4, 5, 6, 7. Excuse me. And the groups likewise are called. And there's a little bit of a difference in the way the groups are named, but the current IUPAC naming of them is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Am I right or wrong? 11, 12, 13, 14, 15, 16, 17, 18. And another way of naming them, sometimes the older way is that we might label them, especially in Roman numerals, 1A, 2A. These are all 3 through 12B. And then we go back to 3A, 4A, 5A, 6A, getting a little bit messy, 7A, and 8A. And one of the reason I point that out, and the reason I kind of like that more, is that by having these numbers, instead of being 13, it's 3, that tells us something about the atom. Do you remember from physical science what the group number, the family number, tells us about the atom? Almost. Yeah. Not extra electrons. Valence electrons. There, we got it. Yeah, the valence electrons. So that's the next thing I guess we'll talk about. I don't know that that was necessarily the next thing I wanted to talk about, but these indicate to us the number of. And this is a terrible mess. Let me stand by while I erase these top ones and start over because they're a little bit too messy even for me. Which that's a pretty low bar. You should kind of be aware of both of the naming systems because they might, I use them interchangeably I was going to say in my life. Whenever I talk about them, I use them interchangeably. And on the test, therefore, they're used interchangeably. And you should just kind of be aware of them anyway. So, and by both of them, I mean 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And also 1A, 2A, 3A, 4A, etc. As an example, I might say name an element from group 14, or I might say name an element from group 4A, and you should be able to know that both of those refer to this. And as I said, the reason I kind of like the older naming style better is that it tells us the number of valence electrons. So back to our atom, back to our arrangement of the atom itself in nature, how many valence electrons does it have? Yeah. Yeah, you can tell that from both. I didn't look and see where you were looking, but you can tell it from my diagram. They're the outermost electrons. The ones in the outermost energy level. Whatever that highest energy level that atom has, the electrons that occupy that are valence electrons. Then you can also tell, the other thing you might have looked at, you can tell from the periodic table. One of the most elegant things about the way the periodic table is arranged is that we can tell how many valence electrons an atom has just by looking at the periodic table. And so where we had phosphorus, which is number 15, which is right here, I'm going to pull this out over here. We'll talk about that in a second. But where we have phosphorus, which has 15 protons, that's why it's number 15. In this nucleus, there would be 15 protons. How many neutrons? Well, we don't really know because that's depending on what isotope it is. It looks like some isotopes of it might have 16 neutrons and some isotopes might have 15. I don't actually know that for sure, but we do know that it has 15 protons. It has to. That's what makes it phosphorus. That's why it's here on the periodic table, is because it has 15 protons. And now even if it loses these valence electrons or gains new ones, it's still phosphorus. It still has 15 protons, and so it's still here. but it might gain or lose valence electrons. And that's why these are so important. These are the most important because they are involved in bonding. We'll talk more about bonding in the next chapter, but bonding is the way that chemical substances change. Chemical substances, which are made of atoms, can combine and recombine to form new substances. Most of the matter that we're familiar with only a very few exceptions, is combined elements. We don't really interact with very many pure elements on a daily basis in our lives. And so it's really important that we understand how they combine and recombine with each other so that we can understand the compounds that are all around us. And the electrons that are used therein, the way that they bind, kind of the method they use to combine is with valence electrons. And as I said, we'll talk more about that in the next couple chapters, how they combine specifically. But these are the important electrons because they're involved in bonding. And that's, again, why the periodic table is arranged this way, so we can tell how they will bond when they bond. Something we can learn about phosphorus by looking at the periodic table. So we can tell its name, phosphorus. I'm drawing here a little square that would represent the square phosphorus would have on any standard periodic table. So we have its name, we have its symbol, we call the letter or letters that represent the symbol. And by the way, these letters are always either a single capital letter or a capital then a lowercase. And that's because since they bond, when we have them in a substance, if we write PO3, which you should know what that is. What is PO3 4 minus? Oh, sorry, PO4 3 minus. No. I've done it wrong. I'll have to cut that part of the video. I don't want to be wrong on the video. PO4 3 minus. How do I know if it's phosphorus and oxygen or the element polonium that there are 4 of? Well, the way I know is where the capital letters are. So even if you, like me, always write in capital letters or mostly in capital letters, you have to be very careful that when you write the symbol of a chemical substance, that you're using capitals when they're supposed to be capitalized and lowercase when they're supposed to be lowercase. So this tells us that this is phosphorus bonded to oxygen, not the element polonium. So the chemical symbol is there, and then underneath that we will usually have the average atomic mass, which for phosphorus is 30.978. 30.978. We talked in chapter 4, I believe, about isotopes. And so this is not, there's no isotope of phosphorus that is called phosphorus 30.978. There's only phosphorus 31, which has 16 neutrons, and phosphorus 30. They're always whole numbers, but the reason this number exists and why it's up there instead of those numbers is because this is the average atomic mass, which is really useful. Because if we have a lump of phosphorus, statistically, some of it will be phosphorus 16, some of it will be phosphorus 31 with 16 neutrons, and some of it will be phosphorus 30 with only 15 neutrons, but they'll be mixed together. And on average, this will be the average atomic mass. And since these atoms are so tiny, we're almost always dealing with a whole lot of atoms, and so the average is a way more important number. Does that make sense? So the average atomic mass is given, and then of course also its atomic number. I probably should be labeling these two things too, but what's this one called? Yeah, the element name, and this one is called the symbol. It might also, depending on the periodic table, yours also tells its, or sorry, not yours, but the one up here also tells its electron configuration. Well, let's just review. What's the electron configuration for phosphorus?
The 1s2, 2s2, 2p6, 3s2, 3p6, and
3p5. No, 3p3, sorry. 3p3. So that's its electron configuration, and that relates back to this. Now I've got arrows crossing arrows. But 1s2, there are 2 electrons. Between 2s2 and 2p6, together there are 8 electrons in the second energy level. And then between 3s2 and 3p3, there are 5 electrons in the third energy level, which is the valence level, which is why it has 5 valence electrons, which is why it's here. We know it has 5 valence electrons because of its electron configuration. and the way its electrons are arranged in space, and because it's in group 15. And that's why these groups exist. Another interesting thing about groups, which is also why they're called families, is just like you and Tommy and your parents, or me and my sisters, less so, yeah, I've got 4 sisters, less so the further we get away from each other in spirit and in physical location, the more apart we get. But there are similarities, right? There's similarities between you and Tommy. I could list them, but I'm not going to. There are similarities between Josie, who's in the afternoon class, and her brothers Gavin and Wade. There's similarities between them. They're in the same family, just like phosphorus and nitrogen and arsenic are in the same family. Are they identical? No. Even if they're twins, you probably know some twins, they're not identical, right? I played poker with Tyler Moreva, who's part of a twins. He's not the same as Taylor. They're not the same human being. They look the same maybe, but they're not the same. So people in a family have similar attributes, but they're not identical. Same as phosphorus, nitrogen, and arsenic, antimony, bismuth, and maybe muscovium would have similar chemical properties, even though they're not exactly the same. And that's because of their number, again, of valence electrons. So these have elements in the same family. I'll use that word. I could also say group, have similar chemical properties. Remember, chemical properties are those properties that govern the way that that element will combine, that it will bond, the kind of chemical reactions it will undergo, and the kind of other elements it will combine with. For instance, this phosphate polyatomic ion, I kind of like this. I keep switching back between 2 different things, but if the objective is to relate the structure of the atom with the structure of the periodic table, I think it's good to kind of go back and forth. So this phosphorus might combine with calcium, for instance. I'm sorry, this phosphate polyatomic ion might combine with calcium. So now instead of having just the phosphate polyatomic ion, we have calcium phosphate. Have you heard of calcium phosphate? Your bones and teeth are made of calcium phosphate. They're a little bit more complicated than that, but this is a compound. Another example of the fact that most of the substances around us, teeth, bones, whiteboard, are made of combinations of elements that are bonded together. So that's why it's so important to know about valence electrons. But the way these combine, the fact that this phosphorus will combine with 4 oxygens covalently, and that polyatomic ion will combine with 3 calciums, 2 of those polyatomic ions will combine with 3 calciums ionically, is governed by how many valence electrons it has. That kind of chemical property is told by how many valence electrons. And a similar thing would happen with nitrogen, the nitrate polyatomic ion, NO3, 1-, right? Will also combine with calcium. Because the phosphorus and the nitrogen, while not the same, have similar properties. They can behave similarly in these. And these 2 substances, you already know, are completely different from each other. But the nitrogen and the phosphorus would have similar properties because of their same number of valence electrons. In fact, whatever differences there are between these are because of how many, mostly because of their mass. The differences in you and Tommy are because of primarily your difference in age. There are other differences, but primarily your difference in age. So similar, or elements in the same family have similar properties that make it so they combine similarly with other elements. And that's really important because the whole study of chemistry is how do these things combine and recombine with each other. That's what chemistry is, matter and its changes. This is matter, and how they change is what we talk about. If we fill in the rest of these, we're not going to fill in all of them, but this is sodium, is that right? Yeah, sodium. I'm going to fill in this whole row. What's a row called? Aluminum. Don't tell me. I'm going to try to get these on my own. Said don't tell me. Sulfur. No, this one's sulfur. This one is silicon. There we go. Now I got it. Chlorine. Neon? Argon. No one cares about these. Why? It's not no one cares.
Because it's like the base of
Yeah, these are
their gas.
they're the noble gases. They don't combine. And that's why a chemist in chemistry class does not really care about the noble gases because we're concerned with how things combine. And since these don't, yeah, we just don't worry about them that much. In fact, these were, as a group, these were the last to be discovered because the rest of them were discovered by their chemical reactions, and these ones don't react chemically. So, wait, I have a mug to prove it. It's freezing in here. Oh, I have 2 mugs that relate to this lesson. Let me get them out of my mug. Let me get them out of my mug drawer. Ooh. That one's kind of a joke. They're noble gases. They're like little knights in shining armor, etc. Asher would really love that one. Where was it? So since these have 8 valence electrons, which, by the way, that is, we're going to write this over here, the octet rule. Most, I'll put it like that. That makes the rule seem kind of like it's not actually a rule when it starts with the word most, but most elements are most stable with 8 valence electrons. Most elements, so most of the elements on the periodic table are at their own personal, no, not personal, oh, maybe, depending on your philosophy of thought, I guess, are at their own individual most stable when they have 8 valence electrons. The exceptions are hydrogen and helium, which are actually stable with 2, because there are only 2 valence electrons. Basically, the rule is a full shell, a full orbital of valence electrons is the most stable configuration. That's why they bond and rebond. We'll talk about that in the next chapter. But the first energy level can only hold 2 electrons, and so both hydrogen and helium are most stable with 2. That's an exception to the octet rule. But the octet rule is named that because most of them are stable with 8. Because even in the third energy level, which can hold 18 valence electrons, when it's the outermost, it only holds 8, if you remember back from electron configuration. So this period is what we were talking about. This period, which is period 3, goes alkali metal. These are the names, and you should probably write these down. Alkali metal, so the whole first group is alkali metals. Then an alkaline earth metal, in this case magnesium. And then I'm going to erase some of my stuff up here so I have room to write. Alkali metal, and then alkaline earth metal. These, it goes through a whole group of what we call transition metals. And then a member of sometimes we call it the boron group. Sometimes we call it the aluminum group. Sometimes we just call it 3A. Sometimes we call it the icosagens.
Which would be one?
Yeah, it's a great question. I would say the most common is probably the boron group. You should, of course, also know that it's called 3A. And then a member of, and then a member of the carbon group, which are also sometimes called the crystallogens. And then these ones do have names. And then a pnictogen, which in our case is our best friend for this video, phosphorus. And then a chalcogen. Pnictogen. Pnictogen is the name of this group, group 15, which contains phosphorus. And then a chalcogen, which in this case is sulfur. And then a halogen, which in the case of our period is chlorine. And then a noble gas, which in our case is argon. And that pattern, alkali metal, alkaline earth metal, boron group, carbon group, pnictogen, chalcogen, halogen, noble gas, is also true for period 2. It's also true for period 4, but with the transition metals in there too. It's also true for period 5, but with the transition metals. It's also true for period 6 and 7, but with another group called the rare earth metals. The rare earth metals, which kind of, I diagrammed it here, but they get squeezed in here. A better way to draw the periodic table, a more accurate way, would be have all of these, which you can't see on camera right now, but I'm indicating the rare earth metals, the F group, the F block. All of these should be squashed in right here. But the reason we don't do that is really just for either aesthetic, we want our periodic table to look beautiful, or practical, we don't want it to take up that much room on the wall reasons. So we usually drag them down to here. There are 2 periods of rare earth metals. So the reason it's called a period is because it goes through the same cycling pattern, a periodical. A periodical is kind of an old-timey word for a magazine or a newspaper, some publication that is issued every so often is periodical. The moon has a period, meaning that it does the same thing month after month, or lunar month after lunar month. I'm sure you can think of other examples of the word period, but those all mean something that cycles, something that continues. And the cycle here of these periods, and why it's called the periodic table, is because it goes through the same pattern. And it's called that because that's how it was discovered. Antoine Lavoisier, one of the great chemists of all time, put the elements that he had discovered in a list. The next guy came along and organized them by atomic mass and said, once atomic mass was discovered, they said, let's organize them by atomic mass. And then they discovered at that time that there was this repeating pattern, this periodicity of alkali metal, alkaline earth metal, boron group, carbon group, pnictogen, chalcogen, halogen, noble gas, and that repeated and repeated and repeated. And so they said, well, let's instead, Dmitry Mendeleev did this. I should write that guy's name. I think it's on your test. Dmitry Mendeleev organized, the maybe apocryphal story goes that he was playing cards, that he had cards laid out in front of him in solitaire, and that led him to the idea of organizing them in this way, where the periodicity could kind of shine through, where you could indicate the periodicity of the elements. Once again, when I say the word periodicity, I mean the fact that they repeat alkali metal, alkaline earth metal, boron group, carbon group, pnictogen, chalcogen, halogen, noble gas, over and over and over again. And he showed that by organizing them as periodic table. And that's his major group, and he did that because he was writing a textbook, and he thought, what's a way that I can get this table of elements organized in a way that will highlight their similarities and differences? And he came up with the periodic table. Of course, at that time, it was still organized by atomic mass, and then when atomic number was discovered, it was organized by atomic number. Which is how it's still organized to this day. So we organize them, even though the atomic mass generally does increase. For any row of elements on the table, of course, the mass does get bigger as we go across the periodic table. But there are exceptions. Tellurium has an average atomic mass of 127.6, and iodine has an average atomic mass of 126.9. And so those two were switched when it was organized by atomic mass. Oops. So then when we reorganized it after Mendeleev by atomic number, it was better because we could see that the properties of tellurium better match the chalcogens than they do the halogens. And the iodine better matches the halogens than the chalcogens. And so those, which are, I'm going to try to draw them on my periodic table, here and here. So those two were flopped. But the properties of iodine actually are a halogen, so it's better for it to be there. So the main benefit to chemistry students of having the periodic table organized this way is that we can easily tell how many valence electrons it has, which helps us later on when we're doing naming. It helps us when we're doing chemical reactions. It even helps us to some extent when we're doing things like stoichiometry, when we talk about the masses and converting that mass to moles, to amount of atoms. Another thing we talked about this in last year, so I'll just remind you that this group here, these first two families, are the S block, because all of these end their electron configuration with an S. Yep. This group here, the transition metals, are the D block. The rare earth metals all end their electron configuration with an F. And this chunk over here are P. So that's another way it's organized. And the fact that they all line up, as it were, where these all, even though it's organized effectively by atomic mass, by atomic number, and then secondarily by valence electrons, they line up to be this way is because of the periodicity of the periodic table. The more you know about how the periodic table is organized, the more you realize how beautifully it's organized, because these things, it's not just a coincidence that the P block also is all these number of valence electrons. It's kind of by design, and that's why, or it is by design, and that's why it's such a feat of human engineering, in my opinion. One of the most beautiful things that human beings ever came up with. Or at least, even if you aren't a huge fan of the beauty of the periodic table, it's at least a way, it's the most organized the human mind has ever been in its elegant simplicity. Another thing that is true of the periodic table that we need, and I'm going to do this one in red, is that there's this stair-step line, this diagonal line that runs down like this across the P block, separating, all of these are what? More specific, not all of them are solids, but they are metals. And that has more to do with than just their state of matter. And then these ones are all, not all of them are gases, but they are all non-metals. They're all non-metals. And then the ones that touch, we sometimes call metalloids, if they touch, like the ones that are right on this, what we call the stair-step line. Stair-step line. Metalloids touch. Except for aluminum. Aluminum is a metal. And then we don't know about these ones down here, whether they are or not. But the reason this is another beautiful way that's organized is that the metals, kind of the way the metals are defined, is that they all form positive ions, what we call cations. And the nonmetals all form anions. They form negative ions. And we'll learn more about that in not this next chapter, but the one after that. Or no, I think it is the next chapter, actually, when we talk about ionic bonding. So it's another way that the periodic table is beautifully arranged. And I hope the more you learn about the periodic table, the more you treasure the many, many ways it's organized, because as you go to it to find this fact, or whether this is a metal or a non-metal, or how many valence electrons this has, you'll be like, I hope you will see, oh wow, it's so nice that it's all just organized like this, and you eventually become, without very much effort, very, very used to how it's organized. Your book does go into some detail about some periodic trends. That is how things are on the periodic table, and that's just another reflection of the beauty of the periodic table, that these things trend periodically, that just like the period went alkali metal, alkaline earth metal, boron group, carbon group, pnictogen, chalcogen, halogen, noble gas, there are other trends in it, like from left to right, the atomic size, that size of the atom actually decreases because there are more electrons and more protons, and they're more tightly bound. So decreasing radii in a period. And there's also, as we go down a group, though, there's an increase of atomic radii. You know what I mean when I say radii?
Yeah, your radius.
Yeah, the radius, how big the atom is, basically. So as we go down a group, they increase in size because they're adding new energy levels. As we go across a period, though, they get smaller, actually. Even though we're adding electrons, we're not adding new orbitals, and we're adding more positive charge in the middle and more negative charge on the outside, so they actually get tighter and tighter and tighter bound. So if we were to draw now instead, even after all this time we've had it up here, we've talked about it many times, if we change this instead of from phosphorus, we change it to the next one, sulfur. it'll actually now have 6 electrons, but they'll be more tightly held. 1, 2, 3, 4, 5, 6, because they'll be more tightly held because there's a stronger positive charge and there's more negative charges, and so whoop, it gets a little bit tighter. So the atom size gets smaller going across. This is, in my opinion, one of the closest times that human beings have ever gotten in their design to something like the beauty of nature. I mean, it's a beautifully organized table. It's a fantastic tool for a chemist of any quality. And compared to my messy little hodgepodge over here, you can see there's so much more information available on an actual periodic table. Even your little paper one has so much information, and it's just such a beautiful thing.